Thanks. I'll begin with a word of prayer. Dearly Father, we thank you for this day. Again, Lord, I thank you for the students and for this time we have just to study your creation. Just pray you to add insight for the students as we study these problems and just help them to just draw together their thinking each day, Lord, just to glorify you also in what they do, Lord. In your name I pray. Amen. All right, so problem number 1. The task here was to find a unit vector such that the rate of change of f at the point 1, 10 is 10. And the function which is given is x squared plus y cubed. So yes, I advised we give a name to our enemy. Let's call the name of it is AB. Now, it's a little bit more than that. And so AB is a unit vector, right? So there's something else we know. We also know that a squared plus b squared is equal to 1, which is very likely the one wrinkle. I mean, that's also something that we insist on, right? So here's the partial derivative of f with respect. I mean, this is fx, right? This is fy. And we get 2x. We get 3y squared. Very good. The gradient, this is okay, but there's just one small thing missing here, which was making me about to say worse things about this than I should, because it's just the gradient of f at an arbitrary point. It's here, right? And then you're like, okay, so that implies if we evaluate at 1, 10, I get 2, 3 times 10 squared, otherwise known as 300. Very good. And then you're reminding me the theorem, which is that the directional derivative of f at the point 1, 10 in the u-hat direction, what is it? It's the gradient of f at the point 1, 10, right? Dotted with u-hat. And so that's why he wrote this here. And of course, this u-hat is really what? AB, which if I forgot who was working on this. I won't call you out by name. But I'm sure if I'd given you like 30 more seconds, you probably would have gotten to the equation I'm about to write down, right? Which was 2a plus 300b equals to 10, right? And a lot of people get to this point in the test and then they get kind of stuck because they forget about this condition, right? This condition right here helps you to actually solve that. If you want to think about it geometrically, what you're looking at is the unit circle in the AB plane, right? And this is like a line. And so it's got to have there's got to be 2 unit vectors that work for it. How do you actually find those? Personally, I'd solve this for A. A would give me 5 minus 150b, right? And then I get a squared plus b squared, which is 5 minus 150b, quantity squared, plus b squared equals to 1, right? Work that out. So what do we got? We've got 25 minus 2 times 5 times 150b plus 150 squared plus 1 times b equals to 1. So what I got here is 150 squared plus 1 times, that's a b squared, sorry, times b squared minus, 1,500 it looks like, right? 10 times 150 is 1,500 minus 1,500b plus 24 equal to 0. This, of course, is a what? You guys don't know? Quadratic, right? You guys know. 22,501 is what this thing is. Very exciting, right? 22,501, the leading coefficient. So at this point, when I have ugly numerics like this, what I will do is I will go to my calculator or appropriate technology, and I will just use the polynomial function a lot of times. Of course, you could use the quadratic equation. I would encourage you to learn how to use the polynomial solver in your little calculator. It's worth your time because you guys are notoriously bad at actually working out the quadratic formula properly using a finite series of calculator steps. It is just a reality, unfortunately. Now, the bad thing is, if you forget where the thing is in your calculator, you're up a creek as well. I'll figure it out eventually. Let's see here. I think it's, I don't know, that's not right. That's a stupid thing.
Which calculator is it?
I've got the Casio FX115ES. I think it's, nah, it's not that one. No. There's a math thing in here somewhere.
Press mode
Yeah,
on your top right and then press 5.
that's the one. Thank you. And then it's 3. So the leading coefficient is quiz points. Minus 1,500. If you remind me after class to look for your card, I'll do it, okay? I'm not going to spend, because right now it'll take me a full minute to find your card, and then I'll feel like an idiot. Anyway, quadratic formula or whatever will give us b equals to 0.04 approximately. Or, what's the other thing? 0.027. And then what's, gotta be careful here. No, go, get out, get me out of here. Calculator. No, let me out. Won't let me out. Oh, gotta go back to mode and hit 1 again, right? I beat you to it though, so I'm not gonna give you anything for that. Let's see here, 1 minus 0.04 squared gives me that, and I square root that thing. So this implies that A is about 0.9992, and I'm probably being not quite numerically. I should probably have kept about 5 decimals on these since they're so tiny. Oh well, it's too late. So what I'm doing, guys, right now is I'm figuring out the other component. Now that I know the B's, I need to figure out what the A is. How do you figure out A once you know B? Right, so that's exactly, so B is going to, A is going to be what? Yeah. And technically, plus or minus that, right? However, when you go back to this equation here, right, I think I need them both to be plus. Is that right? I think I need both A and B to be plus to get a 10 there. For example, so anyway, after some ugly numerics, I get U hat is equal to something like 0.9992, and then the B of 0.04, and or 0.9996 and 0.027. Those check, I think, because basically that's going to give me, let's just check them right quick. So 2 times 0.992 plus 0.04 times 300 gives me 13 point, oh man, son of a gun. Well, I've made a calculator mistake somewhere. Or maybe I just mistaken, maybe it's more likely that I messed up checking the answer. That's kind of my typical error. 0.996 plus 300 times 0.027. There we go. It's fine. It's fine. I'm within. It actually checks. It's okay. When I was checking it, instead of putting 0.99, 0.92, I put 0.992. And that made it look like my answer was off by 4. The decimals here are very picky. You miss one of them, it's way off. So not a very good test question for me, right? I mean, I like things to be kind of like obvious when you're wrong and not because you can't do careful numerics in your calculator, you know? So anyway, is the idea fairly clear here? I mean, you calculate the directional derivative in arbitrary direction, but because it's a unit vector, when we go to find it, that will give us, if it's possible, it will give us 2 solutions on the unit circle. Each one of those correspond to the unit vector, which gives us a directional derivative of 10. But you got to be careful because you're dealing with a quadratic here, so sometimes you add extraneous solutions in the process of basically squaring the equation. Yeah?
So the reason you used a squared plus b squared is because that represents the unit circle?
It's because u hat is a unit vector, and that's the condition for a comma b to have length 1.
Okay.
Right. Now, there are other problems, right? It could be that the analogous equation to this, if you look at the AB plane, it looks something like that. There could be no intersection. That would correspond to the case that your magnitude that you're trying to reach is too big. And so there is no intersection of that line in the unit circle simply because there's no unit vector which makes it happen. All right, 1 down. Next problem here. So not changing. What are we looking for here? Now this is so first of all, she took the gradient, and I think that looks good to me. Partial x, partial y, partial z. Y e to the z squared, x e to the z squared, 2 zxy e to the z squared by the chain rule. Very good. The length of that would be this. Fine. If we plug in the point at the point 1, 1, 0, this, I'm not sure what that means. I'm not sure what to do with that. I'm not giving up on it just yet. It may be something that follows after I look at this. So plugging in 1, 1, 0, we get 1, 1. Oh, that's weird. Oh, it's messed up. So the gradient, this is a very quirky kind of calculation. Look at this. The gradient at the point 1, 1, 0 is 1, 1, 0. Yeah, okay. So what she was doing over here actually is oh, it's almost right. What do we need? Not changing. What's that mean? What's our goal? Our goal is to find u hat, right? Such that that's 0, right? Not changing means the rate of change is 0. So pragmatically, that means we're calculating the gradient at the point 1, 1, 0. We're dotting with some u hat. We want it. So that's what we're looking for. Actually, is some vector which is perpendicular to the gradient vector. This is almost right. Maybe I just cut her off mid-calc. I mean, I think I cut you off, Stacy. So I think you were just about to put a plus here, right? Okay, so with that small modification, the dot product of this and that is 0. So this implies you want u hat equal to, say, something of the form a comma minus a comma b, such that 2a squared plus b squared equals to 1. Oh yeah, I'm sorry. I forgot to warn you. This is a 3-dimensional problem, so you're actually looking at the ABC sphere. If you want to think about it in 3 dimensions, there's like this. You can think about ABC space for your possible unit vector directions. And when we look at the equation, so basically we need this equation becomes, for us it becomes 1, 1, 0 dotted with ABC equal to 0, which becomes the equation a plus b equals to 0. So a plus b equals to 0 is actually a plane. It's a vertical plane like this, and it is going to intersect this. It's going to intersect the sphere of possible ABC directions in some sort of circle. It's a great circle, actually. And the equation of that great circle happens to be 2a squared plus b squared equals to 1. So there are infinitely many u's, in fact. Yes, we could do, in fact, if I put the minus 1 like that, I could put plus or minus this over root 2. Good, those are two possible answers. But in fact, any ABC along that circle would do. That's why this question in 3 dimensions is not as friendly. In 2 dimensions, you just get 2 directions. The one that goes this way, the one goes that way, because when you intersect, the unit circle with a line, you just get 2. But with 3, you're intersecting the unit sphere with a plane, so there's always like an infinity of answers for these kind of questions. Here we go, max rate of change for that. So calculate the gradient. Be careful to do the chain rule, right? Because it's 2 times sine times the derivative of the inside, which is sine, which is going to be the cosine. But then chain rule again, partial derivative of xy pulls out this 2y. So it's a chain rule, right? And again, over here, chain rule. So the first chain pulls out the cosine, the second one pulls out the 2x. But there you go, gradient at xy is this. So the gradient at x naught, y naught, we just plug in x naught, y naught like so. And how would we finish this? What would the max rate of change at the point x naught, y naught be? Yeah, the magnitude of the gradient of f at the point x naught, y naught. So I just have to calculate the square root of 4 y naught squared sine squared x naught, y naught plus 4 y naught. Which one of these? One of these is y naught. That's x naught, right? Yeah. It's just lost in the marker. Let's see. It's fine. It's hard to. It takes a while to get used to writing these stupid things, Sine squared x naught, y naught. And that's not really one of the purposes for the daily quizzes, so that you can get good at writing with whiteboard markers. I think it's a relatively unimportant life skill for most people. But we can factor out the sine squared, right? Oh, shnikes. I lost what? You lost. Yeah, because I cut you off mid-writing. So this is not your fault. This is my fault for not giving you enough time. So sorry about that. But there's a common, well, anyway, let me just simplify my life here. So what we got is we've got 4 times x naught squared plus y naught squared. And they're both having sine squared x naught, y naught, and cosine squared of x naught, y naught. So that's what we get from the sum of the squares of the gradient here. If we were at a point where we knew both sine and cosine were positive, we could get rid of the square root and the square and just leave it with sine and cosine, right? But generally speaking, I don't know what the SIGNs of sine and cosine are, so I'm just going to leave it. I mean, you could rewrite it like this if you wanted to. That would be, maybe this is good for us to do. 2 times the square root of x naught squared plus y naught squared times the absolute value of sine of x naught, y naught, cosine of x naught. Oh, can you guys think of another way to simplify this even prettier? What if I pull the 2 inside? I could actually simplify this a little bit better. See, because I can pull this 2 over here, and then I've got the square root of x naught squared plus y naught squared times the absolute value of the sine of x naught, 2 times x naught, y naught. So I think that's about it. This kind of formula is important if you're, trying to do things like analyze critical points of a function. What's a critical point of the function? I haven't talked much about that in here yet, but yeah. Attendance. Well played, Joshua. Again, you remind me after class to find your card. Someone else in here needs to interrupt Josh's game. You guys are, he's going to have all the points if you guys don't put a stop to this. I mean, somebody else in here has got to I don't know. A critical point is a place where the function's not defined. That's one case. It could be a place where the derivative is not defined. Usually, I usually think about the function being defined there, but definitions vary. Certainly, it's the kind I'm interested in fishing.
Is it a
where the function, where the derivative is. So in calculus 1, we typically say a critical point is a place either where the derivative is not defined or the derivative is 0. And so here, I think most people would say the same, something similar. A critical point for a function of several variables is a point where either the gradient is not defined or the gradient is 0. So, yeah. So sometimes a formula like this would give you some kind of insight as to how the gradient could be 0, right? If the product of x naught and y naught works out to a multiple of pi, that makes this 0, which makes the magnitude 0. The only way a vector can have magnitude 0 is for it to be the 0 vector. So it's kind of a sneaky way to find places where critical points. But of course, you can also go back to the original two equations and say critical point is where both of these things are equal to 0, you know. Now over here, we have kind of a different animal. I gave you the twisted cubic, t squared, t cubed. And I said, look at the composite of it with the function cosine x plus y plus z squared and calculate the derivative. So you did what any good calculus 3 student who has not been taught the chain rule yet would do. You compose the function. So you're like, well, this is really just cosine of x plus y, which in this case is t plus t squared. Very good. And then z squared is actually t cubed squared, which is t to the 6th, right? Because you've been watching me write stuff too much, you put some unnecessary parentheses here. I blame myself for that. And then you differentiated. So, which is 1 plus 2t minus sine of t plus t squared, chain rule, very good. 6t to the 5th, bingo. Now, one of the things I wanted to teach you guys today is that this is part of a general pattern. So there's a chain rule. If we have the derivative with respect to time of a function of several variables composed with a path, say r of t, like this, all right? There's a chain rule in this context which is quite beautiful. What it is it's the gradient of f, all right? The gradient of f evaluated at the space curve of the path r of t, and then dot product with the velocity dr dt. So this is a chain rule for the composition of a path and a function of several variables. So to illustrate this for this problem, the gradient of f was what? We got minus cosine of x plus y, minus the sine of x plus y, 2z. And so the gradient of f evaluated at r of t, which was what? T squared, t cubed, would be minus cosine of t plus t squared, minus cosine of t plus t squared, and 2z cubed. Oh, sorry, 2t cubed. What's the velocity here? dr dt? It's just 1, 2t, and 3t squared. So when we calculate the gradient of f at the space curve, at the path r of t, dotted with the velocity dr dt, what do we get? We just get minus cosine of t plus t squared, minus 2t cosine of t plus t squared, and then plus 6t to the 5th. And you're like, well, I'm glad you've shown me this chain rule, but clearly my way was easier. That's true. Yes?
Why does the cosine stay the same, but the sine change to a cosine? Where does the negative come from?
Why did the sine change to a cosine? I think that the main reason is that that's wrong. Let's see here. Which one is wrong? Oh, interestingly, there's 3 things wrong here, 1 thing right. Let's see if we can fix it. All right, so you take away all my points. Fair enough. Obviously, the derivative of cosine is minus sine, yes? And then the chain rule is kind of boring. It just spits out at 1 here. So that's supposed to be minus sine. As was this and this. So, and all of the negative signs are from the derivative of cosine being minus sine. And now you can see that if you compare this answer and my chain rule based answer, we get the same thing. The chain rule is nevertheless, I mean, for a specific problem like this, fair enough. It is easier to just, plug in the thing and differentiate. But there are theoretical discussions that we'll have in here where that chain rule becomes important, and you need to know about it, all right? So I need to show you guys a couple things today. So our major course of action right now is to try to understand directional derivatives and also the gradient, right? And so I've been working a lot of problems in here. We're about to go over the next kind of theory arc in here, which is built off all these calculations. But the next major thing I need to show you is just, what is the gradient vector? What's it look like? And a second here. So here's a bunch of examples. We're pretty much, I'll talk about this. I'm going to talk about this pathological stuff some other day, probably tomorrow. The end result of that discussion is that if we assume the function is continuously differentiable, which just is fancy math talk for saying both of the partial derivatives exist and they're nothing weird, then in that case, the formula I keep using makes sense. In particular, the directional derivative in the AB direction of the function f at the point x naught y naught is just given by the gradient at x naught y naught. You might need to zoom out, Emily. Oh, here, I'll do that. Opposite of what I want to do. There we go. So this formula up here assumes that is definitely true if the function's continuously differentiable. If the function's not continuously differentiable, if weird stuff goes on where the partial derivatives exist but are not continuous, then all bets are off and all kinds of weird behavior is possible. Essentially, the underlying cause is these weird new multivariate limits where you can approach different ways in different directions and get different results. Essentially, the directional derivatives are based on like a kind of path limit, because they just consider the x not being fixed or y not being fixed and varying along that path. So we'll be able to exploit that to come up with weird examples. Anyway, enough about weird examples. I have told you these things already, just trying to emphasize and draw them together here again. If we want the direction of maximum increase at a function, for a function, and we have the gradient is non-zero, right? If this was 0, then I tell you to point in the direction of the 0 vector for maximum increase. It doesn't really mean much, does it? So this text box here assumes that the gradient's non-zero to make meaningful comments, right? But certainly, when we align with the gradient, we get the maximum increase. When we're exactly opposite direction to the gradient, we get the maximum decrease. And if we're at theta equals pi over 2, in other words, if the gradient vector is like this, and your u is like this, then you get rate of change of 0, right? Which is like problem 3 here. I mean, problem 2, I think. I just covered up with the board, right? That was an example of that. Any u hat, which is 90 degrees, with respect to the gradient vector, is going to give us a rate of change of 0, which is to say that along that direction, the function remains constant at such a point. So this example 4.227 is much like the ones I've had you do at the start of class, problem 1, right? problem, example 4.228 is much like problem 2, except it's a two-dimensional one. You know, find a point at which this function is constant in all directions. So that would mean what? Oh, I think that would mean, what that means is the gradient has to be 0. And when you work that out, that's just going to be the origin, because twice x naught, twice y naught is 0, 0. So the origin is a critical point for this function, which is not especially surprising if you think about z equals x squared plus y squared, right? That's the hyperboloid which opens up. You know something funny is going on at the origin, right? Anyway, critical point is a point where either the gradient does not exist or it's 0, as we were talking about. So here's another example or two about that. So I've kind of rolled a lot of the examples in here into daily quizzes, and I hope that's okay with you guys. But you should also realize that just because I don't cover in here doesn't mean it's not worth reading, right? You'll gain additional insight from reading those. But that brings us to our next kind of major topic, which is that if f is differentiable on U, which is just some subset of R2, the gradient of f defines what's called a vector field on U. What is a vector field on something? A vector field on some object is just you attach a vector at each point along the object. That's a vector field. So we could talk about a vector field along a curve. We already did that. Like the TNB frame is a vector field. Just T is a vector field. I attach the unit tangent vector at each point along the curve. That's a vector field along curve. You can look at other things. Like we could look at, here's a very standard example. Think about the temperature in this room, right? You could calculate the gradient vector for that temperature function at any point. And the direction of that gradient vector would point you what? It would point you in the direction of increasing temperature at that point. So, but if you think about it, the whole room, right, has points, and each one of those points you can attach a vector to. So that, what I'm just describing, would be a vector field in 3 dimensions, right? But this concept of vector field is a more general thing than just vector field in a plane or on a curve. It's just any kind of object you like, you can attach vectors to, and it's called a vector field, all right? Here's some pictures, though. So the other thing is we can visualize vector fields by drawing the plane or whatever we're looking at, and then like actually looking at the vectors. So here's x squared plus y squared. And these pictures, let me describe. There's a couple things going on. The one thing is that I'm drawing the vectors in green. Well, not me, Maple. But the other thing is these circles. These circles are what are called level curves. Level curves for the function that we're looking at is when we take f of x, y and set it equal to a constant. This defines a level curve. I'll talk more about that tomorrow, but these are the level curves. So you notice something about the relation of the gradient vector field, which is green, in the level curves. Do you see what the relation is? They're perpendicular. So there's the gradient vector field for x squared plus y squared. This is the gradient vector field for x squared minus y squared. Those are the level curves, hyperbolas, right? Always perpendicular. Here's another one, though. Here's the gradient vector field for a very boring function, x. F of x equals to x. What's the gradient? It's 1, 0. What's the gradient vector field to x? It's just x hat, which, by the way, x hat is not just one vector. It's actually the application of a vector 1, 0 at every point in the plane. This is x hat, actually. It's a vector field. Y hat is a vector field, right? And so if you look at that, that actually gives us a way to derive the unit vector fields in the direction of r or theta. What we want is to take the gradient of r, or the gradient of theta, and normalize it to length 1. That gives me r hat and theta hat. So in fact, the gradient of r works out to this. We did this calculation, daily quiz last time. We got x over r, y over r. My secret reason for putting that up here. And, well, that does not have length 1, right? That has length 1 over, or does. That has length 1, doesn't it? What's the length of x over r plus comma y over r? Square root of x over r squared plus y over r squared, which is x squared plus y squared over r squared, otherwise known as r squared over r squared, otherwise known as a vector of length 1. This already has length 1. On the other hand, the gradient of theta ends up like length 1 over r. So you have to multiply that by well, you have to divide by r in order to give it length 1. Anyway, I just wanted to show you a few of these pictures while I'm up here, and we'll look more of them tomorrow. Eventually, the same thing allows us to define, y hat, z hat, and more funky things like the cylindrical radius unit vector, or the theta hat in 3 dimensions, or the, worse yet, the colatitude. Oh, look at this. Awful. Look at these things. All right, anyway, I shut up. Thanks, guys.